In this video, we're going to look at the limiting reactant in a chemical reaction. So in a chemical reaction, the masses of our reactants are going to decrease over time as our chemical reaction proceeds. And then we're going to begin to form a product or products, and so the masses of our products will begin to increase. So this process will continue to occur, and we'll continue to make product until at least one of our reactants is all used up. When one of our reactants is used up, the reaction can no longer proceed and the reaction is complete. The limiting reactant in a chemical reaction is defined as the reactant that runs out first. It's the reactant that stops the chemical reaction, and therefore it limits the amount of a product or products that can be produced. The excess reactant, on the other hand, is the reactant that is not completely used up, so you're going to have some of it left over, and it's the reactant or reactants other than the limiting reactant. So to illustrate the concept of a limiting reactant, let's look at this simple analogy. Here we have the parts to make a car. We have a kind of a chemical equation here, if you will. One car body will combine with 4 tires to produce one complete car. If you have 8 car bodies and 48 tires, how many complete cars can be produced? Well, 48 tires, that's enough tires to make 12 complete cars. 8 car bodies, well, that's enough to make 8 complete cars. So if we start to make our cars, we know that the car bodies are going to run out first. So that means that we can only make 8 cars and we'll have 16 tires left over. So another way of saying that is fewer cars can be produced from the amount of car bodies that we started with than with the amount of tires that we started with. So our car bodies, we can say, are limiting, kind of like our limiting reactant. They're the reactant or the substance that runs out first. The tires are our excess reactant, or at least analogous to our excess reactant, because they're the substance, our reactant, that does not run out. So we have some of it left over. Another thing, the car bodies, when they ran out, we could not make any more cars. So the car bodies, the limiting reactant, determines how many of a product can be produced. So let's take a look at a problem involving chemistry. Iron reacts with molecular oxygen to form iron 3 oxide, also known as rust. Take a second, pause the video, see if you can write the balanced chemical equation, and then read through the question and give it a try. See if you can solve this part A and B before I work through it with you. So pause the video, give it a try, and then I'll go through it with you. Okay, so first thing, iron reacts with molecular oxygen to form iron 3 oxide. Then we need to balance that chemical equation. So this tells me that, that 4 moles of iron will react with 3 moles of oxygen to form 2 moles of iron 3 oxide. Now, one thing I want to point out to you here is that in the problem, in the question, we're given a mass of iron and a mass of oxygen. So we're given a mass of both reactants. When you come across a problem where you're given the mass of both reactants and asked to figure out the theoretical yield, you have to treat this as a limiting reactant problem. So we have to figure out which of these reactants will run out first, iron or oxygen. So how do you do that? Well, one way to do that is determine the theoretical yield of the product from the mass of iron that we are given, and then determine the theoretical yield of the product from the mass of oxygen that's given. We compare those two theoretical yields. The reactant that produces the smallest theoretical yield is the limiting reactant. Remember, only one of our theoretical yields is correct, so we have to clearly indicate which one of them is our answer. Much like with the car and the car bodies and the tires, we could not produce both 8 and 12 cars. We could only produce 8 because our limiting reactant determined how much of the product could be produced or cars could be produced. So let's determine the theoretical yield of iron oxide from the mass of iron that we're given. You can see this is a basic stoichiometric calculation. We convert our grams into moles, our moles of iron into moles of iron oxide. Our coefficients came from our balanced chemical equation, and then we convert moles of iron into grams of iron. So if iron is my limiting reactant, I'll be able to produce 7.82 grams of iron oxide. Let's compare that to oxygen. 1.95 grams of oxygen, convert it to moles, and then convert it to grams of iron 3 oxide as we have here. So my grams of oxygen will allow me to produce only 6.49 grams of iron 3 oxide. So now remember, I cannot produce both 7.82 grams and 6.49 grams of the product in the same chemical reaction. Only one of these is correct, and that's going to be the smaller of the two. So we would say that 6.49 grams of iron 3 oxide is my theoretical yield. The 7.82 grams, well, that's meaningless, so let's cross that out. So since the mass of oxygen that we're given produced less product than the mass of iron that we're given, we could also say that the oxygen is the limiting reactant. The oxygen is going to be used up first. So all of that 1.95 grams is going to be used. The iron is the excess reactant, so we're going to have a little of that left over. So part B asks, how much of the iron, we know that's the excess reactant, how much of the iron is going to be left over when the reaction's complete? So to do this, let's determine our strategy. I would use the mass of the limiting reactant, oxygen, to calculate how much of the iron was used. Then we could subtract the mass of the iron that was used from the mass of iron that we were given, and that will tell us how much we have left over. So I'm going to take the mass of oxygen that I'm given, convert it to moles, use the balanced chemical equation. 3 moles of oxygen will react will react with 4 moles of iron, and then convert moles of iron to grams using the molar mass. So this tells me that 1.95 grams of oxygen will completely react or use up only 4.54 grams of iron. Remember, our question, part A, told us that we were given 5.47 grams of iron. We calculated just now that we used 4.54 grams. So we're going to have a little bit of iron, 0.93 grams, left over unreacted. So that'll be our answer for part B. Now, one other thing I want to point out to you is that this chemical reaction must follow the law of conservation of matter. So I set up this little table here. These are the masses of iron and oxygen that were given in our problem. And of course, the product, we didn't have any of that at the very beginning because the reaction hadn't started. When the reaction went to completion, all of my oxygen was used up because that's the limiting reactant. We calculated that only 4.54 grams of the iron was used. And so when the reaction was all done, we had 0.93 grams of the iron left over. We had no oxygen left over. It was all used up. And we produced 6.49 grams of iron 3 oxide. So how can we use these numbers to demonstrate the law of conservation of matter? Pause the video just a second and think about that. How can you determine that this did in fact follow the law of conservation of matter? Well, we know that matter can neither be created nor destroyed, so the mass of reactants that we used must be equal to the mass of products that we produced. So how much of the reactants did we use? Well, we used 4.54 grams of the iron, 1.95 grams of the oxygen, and we produced 6.49 grams of our product. So if we add 4.54, 1.95, we get 6.49. So indeed, no matter was destroyed. It was all conserved. So let's take a look at another problem. Pause the video, read over this problem, and see if you can solve it, and then we'll go over it together. Okay, so first of all, let's take a look at part A. What mass of ammonia can be produced when 3.25 grams of hydrogen and 8.95 grams of nitrogen are reacted. So the first thing I want you to appreciate is that this is a limiting reactant problem because we are given the mass of both reactants, both hydrogen and nitrogen, so we have to figure out which one of these is going to run out first. That is going to determine the mass of our product that can be produced. So we solve this just like we've discussed before. We pick one of our reactants, doesn't matter which one first. Here I've picked the hydrogen, so I take the 3.25 grams of hydrogen, I convert it into moles using the molar mass. Then I convert moles of hydrogen into moles of ammonia using my balanced chemical equation. Then I can convert moles of ammonia into grams of ammonia using the molar mass of ammonia. So if hydrogen is my limiting reactant, then I will be able to produce a theoretical yield of 18.3 grams of ammonia. But I don't know if hydrogen is my limiting reactant. I have to take the other reactant, the nitrogen. 8.95 grams of nitrogen, convert that into moles using the molar mass of nitrogen. And then I use my balanced chemical equation coefficients to convert moles of nitrogen into moles of ammonia. And then I use the molar mass of ammonia to convert those moles of ammonia into grams. So you can see if nitrogen is my limiting reactant, I'll be able to produce 10.9 grams of ammonia. So because the nitrogen, the 8.95 grams of nitrogen, gives me a lower theoretical yield of ammonia, that tells me that nitrogen is my limiting reactant, and the ammonia, the 10.9 grams of ammonia, is my theoretical yield. Okay, so I compare the two yields from hydrogen and nitrogen, and the one that gives me, the reactant that gives me a smaller theoretical yield, is my correct answer. So 10.9 grams of ammonia can be produced. The 18.3 grams of ammonia that I calculated from the hydrogen is meaningless. That cannot be produced in this reaction. Again, only one amount of product can be produced. So let's take a look at part B. What mass of the excess reactant can be produced? Well, we said that our nitrogen is the limiting reactant. So I need to take the nitrogen, and of course that's going to make hydrogen my excess reactant. So I'm going to take the nitrogen, the 8.95 grams of nitrogen, and calculate the mass of the hydrogen that is actually used in the reaction. You always use your limiting reactant in these calculations. So I take my mass of nitrogen, convert it into moles of nitrogen, use my balanced chemical equation to convert that into moles of hydrogen, my excess reactant. Then I take the molar mass of hydrogen to convert that into grams of hydrogen. So 1.93 grams of hydrogen is used. 1.93 grams of hydrogen is needed to react with the 8.95 grams of nitrogen. So be sure you understand why we're doing these calculations. Now that doesn't tell me how much is remaining, but I know I started with 3.25 grams of hydrogen. I used 1.93 grams of hydrogen from that calculation. So if I subtract those, I figure out how much hydrogen was not reacted, how much is remaining. So 1.32 grams of hydrogen will be remaining. So be sure you can recognize a limiting reactant problem. Be sure that you understand the strategy for solving it, and you can do that. So be sure you practice lots of these problems and get proficient at them.